Bulvinaka everyone. Today I'll be discussing or illustrating of the poster that I've created using the Microsoft Publisher. The instrument that I'll be discussing or illustrating on the poster is the ultraviolet visible spectrophotometer. So the purpose and the main concept of this poster illustrating a video presentation is listed below here. Firstly, it is to know what are the components of the ultraviolet visible spectrophotometer. Secondly, what the instrument is used for. Thirdly, the process in using the spectrophotometer. And lastly, how the calibration graph is plotted by using this kind of instrument. So as you can see here, this is the poster that I have created using Microsoft Publisher. And this is the ultraviolet visible spectrophotometer. As you can see here, this is the LCD panel. This is where you get the readings of the absorbance values being detected. And at the bottom of the panel is the buttons, the setting buttons. Just at the bottom of the screen is the wavelength setting knob. This is to set a suitable wavelength for the solution that is going to be placed in this sample compartment. Just below the sample compartment is a black knob. This is the holding changing knob. This is where when it is pulled, it goes according to the placements of the cuvettes being placed in here. So basically, the ultraviolet visible spectrophotometer, it is used to measure how much light is being absorbed in solution with different wavelengths. It has a sample compartment, as I have already discussed, that is on the left side. This is where cuvettes of place solutions with different concentrations are taken into measurements of their absorbance being detected. So according to cuvettes, this is how the cuvettes look like. They are placed here in the sample compartment. So a cuvette usually has a length of 1 centimeter by 1 centimeter, and they have opposite sides that looked frosted. They have frosted appearance, and the other opposite sides are clear. The cuvettes are to be handled carefully because they are expensive, and also to avoid scratches or fingerprints on it. In avoiding the scratches and fingerprints, these can disperse the light away from the detector, or this can take away the light from absorbing the light in the cuvette or in the solution. So while placing the cuvettes into the sample compartments, it is being suggested, or it is being told by the lab constructor in our experiments, during our lab experiment, that we are supposed to hold the cuvettes by its frosted sides. This is to avoid the fingerprints and scratches or drop marks. And also, before placing the cuvettes in the sample compartment area, these are to be wiped carefully with a Kim wipe or a clean tissue paper. So on the other side of the poster, this is the processes that are happening inside the spectrophotometer. So firstly, there's a source, there's a light source. So usually in a ultraviolet visible spectrophotometer, the light source can be a tungsten lamp source, and this usually has a wavelength of of 350 to 2500 nanometers. So this is how the processes look like from the light source, the tungsten lamp source. The light of it goes through the entrance slit. So from the entrance slit to the dispersing device and then to the exit slits, these three are components of the monochromator. So the monochromator basically helps to disperse light and also to select a selected wavelength from that single wavelength. So as the light passes through the entrance slit, it touches the dispersing device. The dispersing device can either be a prism or a diffraction grating. So just by its name, dispersing device, this means that from a single wavelength of a light, it helps to disperse light into different values of wavelengths. So different values of wavelength, that suggests that it has different colors as seen over here. So this different colors wavelength, it reaches the exit slit, and from the exit slit only one single wavelength is selected, a suitable wavelength that is being absorbed. So that is gone through or is passing through the cuvette that contains the solution in it. So this wavelength or this light intensity being absorbed here, this is known as IO, and the light intensity after that, passing after it has been absorbed, is known as I. These two gives equation IO divided by I gives you transmittance, and the transmittance can be calculated by the equation of absorbance equals negative log of transmittance. So once the light intensity is being passed through the solution in the cuvette in the sample compartment, it is then deducted onto the detector, and the absorbance value or the light being absorbed with its wavelength is being measured or is being seen on the LCD panel here. So the analytes that are able to be dissolved in solvents are suitable for this type of analysis, and the analytes would need to absorb the UV or visible lights. Compounds absorbing the UV lights have a UV visible spectrums. If the UV VIS spectra of compounds are different from another, then there can be an analysis of the mixtures. So according to Beer's law, the concentration of a solution has a linear relationship with the absorbance that is being absorbed by the solution. So in accordance to Beer's law, as you can see here on the bottom right corner, there are different solutions here with different colors, and with these different colors they have different wavelengths. Here, as you can see. So from the red solution here, it has a wavelength of nearly 600 nanometers, as opposed to the dark blue one that has 650 nanometers, and it goes on to the other solutions, other colored solutions, as you can see here. So this is an absorption spectra, and from the absorption spectra, a Beer's law graph can be created, according to concentration and absorbance of a solution. And this is shown on the next slide. So as you can see here, this is an example of the calibration graph. So as discussed before, the concentration and absorbance, they both have a linear relationship towards each other. Therefore, they are both dependent on each other. So since they have a linear relationship, they have a straight line that is being shown here on the graph by its points that are being placed here. So according to Beer's law, or according to its equation, absorbance equals molar absorptivity by path length by concentration. It goes well with the equation y equals mx plus c. So from the graph that is shown here, according to y equals mx plus c, this is how it looks like. Y equals 1.32x plus 0.004. So the y corresponds to absorbance and the x corresponds to concentration. So this graph as well, according to an unknown solution, you can calculate the concentration of an unknown solution just by looking at the absorbance value that is being detected by the spectrophotometer. So with the absorbance value, you can place it instead of y, and you can find the concentration just by making x the subject of this equation here. Just at the bottom of the equation is the r squared value. R squared value indicates of how the points are being passed through, and they have created a straight line, so it has a best fit of regression line. So it is stated that the more the r squared value is closer to 1, it has the most best fit of line just going across the graph that is shown here. So it is shown that the r squared is equal to 0.9969. So it's closer to 1, meaning it has the best fit of line. So best fit of line indicates that it is a straight line. So this is a straight line, indicating that it has a linear relationship. So therefore, absorbance and concentration, they're dependent on each other. That is the end of my presentation, and hope you guys have enjoyed it. Nakabakalev, God bless, take care, and stay safe.